Good afternoon, everybody. Welcome back to Discrete Math. Plan for today is we have presentations on the Euler Circuit 2 packet, and then I have the final packet of the semester for you to pass out after that, Euler Circuits 3, where we're finally going to answer the question once and for all. Does the Königsberg problem have a solution? Usual office hours today after class, tomorrow morning at 10, tomorrow afternoon at 1. Tomorrow morning, cutting it a little bit short because we have a faculty meeting. As far as homework goes, we'll have presentations Friday on Euler Circuits 3, and also don't forget portfolio due Monday. So I'm going to try and get out your final exam to you on tomorrow sometime. If not, it'll definitely be out on Friday. You'll have a week to work on it. Just like with the midterms, you can work with one partner if you so choose. If you would like some help finding a partner, let me know and I will do my best to play matchmaker for you. Any questions or comments before I get started for today? All right. Why did the geometer make such a big mess in the oven? Because when they put their food in the oven, they followed the instructions of putting it in at 180 degrees. All right. Let's see what we got here. Yes, give her that. I suppose Alex can go.
I'll take a stab at the last one, Dr. Gersel.
I was about to say, nobody signs up for a problem for the first time, trying to embarrass me in front of Dr. Trelaw here. Let's see. We'll give one to Holly. And, all right, so Olivia, you want to kick things off for us?
All right, so I had part A of the odd vertex theorem on page 1. So we are going to suppose that A is an odd vertex in Euler graph G, and then we're trying to prove that an Euler path that starts at A cannot end at A. So what I did first was say that there exists an Euler path that starts and ends at A. And then if this, so this is like kind of contradiction. So if this is so, then the degree of A must be at least 1 plus 1, because if you start at A, then there has to be an edge, and then if you end at A, there also has to be another edge. So there has to be at least 2 edges connecting to the vertex, making the degree of A at least 2. And then if you do this leaves an odd number of edges connecting to A. So there would be enough edges to leave A, but not enough to come back, meaning there's no path leaving and coming back to A. Thus, you can't have an Euler path starting and ending at A. So just an example to kind of like illustrate this. So obviously there's like a path from A to B, B to C, and then C to A, and then in order for there to be a path, you'd have to use this edge here, but then you wouldn't end at A. So not saying that it only works for this example, but in general, like that's just kind of illustrating it. Are there any questions? No?
Any questions for Olivia about her proof? Thank you, Olivia. So, we have Holly for part B.
All right, so my proof is very similar to Olivia's. So I had proved that every Euler path that starts or ends at A. Sorry, I guess I should start with, we're supposing that A is an odd vertex in the Euler graph. And now we prove that every Euler path must start at end or at A, which is the odd vertex. And so, like Olivia, I won't write out my whole proof because I'm pretty sure everyone said something similar. So by contradiction, we're going to assume the Euler path does not start or end at A. So this would imply that it leaves A and arrives at A the same number of times. So it implies that the degree of A is even. But this contradicts our original assumption that the degree of A is odd because it has shown to be even because it has to enter and exit A an even number of times. So thus, by proof of contradiction, every Euler path containing an odd vertex A must either start or end at A. And so I can write out this example that we did in the Euler circuits packet, where it's basically saying the same thing as what I was proving. So we can see that the degree of A and the degree of C is odd. They both have 3 edges. So when we start at an odd degree, we can go like, let's say A, B, C, D, back to A, and then we need to complete this other edge, C. So we're starting at an odd degree, and we're also ending at an odd degree. And you can do the same thing if you start at C and then you go back to A. So, any questions? Okay, cool.
Thank you all. All right, even vertex theorem, Adam.
So I think I'm going to start out just drawing a picture because that's how I thought of this one, and then I'll move to the more general case. Because if I don't write the picture, draw the picture out first, I'm going to confuse myself, and this is just going to be really uncomfortable. So kind of how I thought of this one is, suppose we just have some odd vertex, or even vertex, B, some graph that looks something like this. Really simple, right? And we want to start a path, an Euler path, at B. Well, it's an even vertex, so we have an even number of choices. So I said, let's just choose this edge between B and A. So essentially, if we move this way, we only have so many remaining edges available, right? We couldn't go back the same way because this is a path, right? So it's kind of like we've almost lost an edge a little bit. You can kind of think about it like that. It's almost like this. This is how I kind of imagine what we're left with. G's down here. And then I said, okay, let's just pretend that this is what we started with. So let's now pretend we have this graph and we're starting from A. Well, then we see that we would have to end up at B by the odd vertex theorem because this is an odd vertex. That is an odd vertex. So if this is our graph and we want an Euler path and we start at A, we'll have to end at B. So that's kind of how I imagine what was going on. I'm like, if we have something like this where we have an even vertex and we start, once we leave that even vertex, we're going to have an odd number of edges incident with that vertex remaining that will have to be traversed at some point in the path, right? And so if we think about, okay, let's say we have an Euler path and we're going to start an even vertex and we take one of those even vertexes, that means we'll only have an odd number of edges incident with that original vertex that will be remaining for us to take the path. Now we know that it's impossible for us to take all of these edges in the middle of the path because that would mean the number of times we enter that vertex, the number of times we leave it in the middle of the path would be odd, which is impossible. So we know that if we start at an even vertex, an Euler path, starting from that even vertex, it will have to end there as well. So again, I know it's really wordy. This is really what kind of guided my thinking, something like this. And obviously you could make this more interesting. If you had other edges, it remains the same. That it's kind of like, okay, once we leave this even vertex, it almost kind of becomes an odd vertex in terms of remaining edges because we can only take each edge once. So, does that make sense? I know it was really wordy. I can only imagine it like in the picture sense, and the words were harder. So, okay, I'm getting nods, so that's good. Alex doesn't look like he's like wanting, like just thinks I'm an idiot. Yeah, Lily?
So is this true only for Euler circuits? Could you have an Euler path that's not an Euler circuit that starts and ends at an even vertex?
Well, we know that if an Euler graph has odd vertexes and that there's also an Euler path, we're going to have to start at one of those odd vertexes. So I don't think we could have the case where we have an Euler path in a graph with odd vertexes where the path does not start at one of those odd vertexes. Because I mean, later we show that it has, an Euler graph with an Euler path has to have 0 or 2 odd vertexes. So we didn't start, and then we already covered the start stop thing. So I would say no, but maybe. I don't think so, but that doesn't mean much. So
Stay tuned for later this class.
Dr. Gerstle,
What's the plural of the word vertex?
vertices? Did I not say that? Oh, well, I'm illiterate.
He said vertexes about approximately 15 times.
Really? I did not notice that. Oh well, I'm a math major. Darn. Vertexes. Well, I don't know. You can just make a new word.
I'm sorry?
I'm just creative.
I did the same thing yesterday in office hours. I kept saying vertice as the singular.
Matrices, like I have to, like that's a hard word for me. Like matrices, so it just matrices.
Okay, any other questions for Adam? Nice job. Next up, we have the first Euler path theorem.
Yes.
This would be a second.
I'm a little nervous to try and prove this, seeing as no one else signed up for it, but it's worth a shot. So the first part of the first Euler path theorem that we have to prove is if we have a graph that has an Euler path, is it connected? All right. And I think you can just do this via contradiction, like some of the other proof that we've seen today. So if you suppose there's an Euler path and that it's disconnected, that means that one, by the definition of an Euler path, there's a path through every edge and consequently through every vertex.
Thank you.
Nailed it. Vertexes. There you go.
Right. But secondly, if it's disconnected, then there exists some x and y, some vertices in the graph G, such that there isn't a path from x to y. But notice in the first premise of this how if there's a path through every edge which hits every vertex, then if we wanted to find a path between two arbitrary vertices, all we would have to do is start on this path at x and just follow it to y, okay? And if y comes before x on this path, then we could just go the opposite way. And so what you get here is a contradiction. And thus, a graph with an Euler path has to be connected. For the second part of the proof, an Euler path has to have all of its vertices either being of even degree or two of the vertices have odd degree. So the way I thought about this was there's two possibilities for the Euler path. Either one, it starts and ends at the same vertex, or two, starts at x and ends at y. Where vertex isn't equal to y. So it starts and ends at a different vertex. If the Euler path starts and ends at the same vertex, then for that first vertex, that origin vertex, which is also the concluding vertex, we use up 1 degree, 1 edge, and leaving that vertex initially. And then every time we traverse through that vertex on the path, actually, sorry, that wouldn't happen. Never mind. And then we end at the vertex. So we use 2 degrees by starting at the vertex and then, oh, no, sorry. We can repeat, we can't gap. So, sorry, I'm getting myself confused here. So we use one edge to go from the starting vertex, and then each time there's an edge that passes through, or there's an edge that goes to that vertex, we use up 2 degrees to traverse through that vertex, right? 1, 2, 1, 2. And so we use up an even number of degrees in order to traverse through that vertex every time we go through it. And then to conclude at that vertex, we have to use up another edge. But since, again, we end at that vertex, we wouldn't use up an even number of degrees in that case. And then for all of the intermediary edges, we're passing through them. So each time we pass through them, each time we traverse them, we use an even number of degrees. And so it's just going to be adding, you don't have to add here. I don't know exactly where I was going with that, but each time, so we know for that origin vertex, it's going to have an even number of degrees because this is just going to be 2k plus 2, which is even, and then each of the intermediary vertices has to have an even number of degrees because we pass through it, right? So in the case where the Euler path starts and ends at the same vertex, it would have all even degrees, so it would have 0 odd vertices. But what if it starts at one vertex and ends at a different one? Well, in that case, the origin vertex, we use up 1 degree to get off of that vertex. Every time we pass through it, we use up an even number of degrees. Okay, so that vertex would have an odd number of degrees. And then every intermediary vertex has an even number of degrees using a similar argument up here. And then the ending vertex has an odd number of degrees because every time we pass through it, we use an even number of degrees. But when we conclude at that vertex, we only use 1 edge to end at it. And so again, there's it would be odd here. So this is the end. This is the start. And plus 2k. This is very messy, but my apologies. I hope by verbalizing what I was trying to write down, it made a little bit of sense. But in the end, we arrive at the conclusion that if the graph, if the path ends at a different vertex, then we have 2 odd vertices. And since these are the only 2 options we could have for an Euler path, then that's exhaustive. Okay. By the way, also, you know that the starting vertex has an odd number of degrees because we can conclude that by the contrapositive of the even vertex theorem. Okay, any questions? Griffin?
So step 1, that is assuming that a circuit is a type of path. Because of it, yeah? Cool. That's all.
Okay.
I actually have a question about the first part. So, Suppose we have, kind of go with Adam's example of the 4 vertices that were connected by 3 edges, the square that had the 1 edge missing. There doesn't exist a path from those 2 vertices, but yet there still does exist an Euler path, right?
Lily, would you mind going up and drawing what you mean?
I'm not sure, I could be missing something. But if we have there doesn't exist a path from X to Y, but there still exists an Euler path in the graph. I didn't know, is that, because I guess you said there exists an X and Y in the graph such that there doesn't exist a path from X to Y, which is a contradiction, but there doesn't exist a path here in the graph, but there still is an Euler path around, I don't know.
Well, in that case, the Euler path is the path from X to Y.
I guess you're right. I guess I was just thinking a direct connection. I was
Are
just
you
a little
thinking of like
confused.
edge instead of path?
Yeah, I was thinking of
Oh, okay, I see what you're saying.
Yeah, there could be a path between 2 vertices, even if those vertices aren't directly connected by an edge. That just means you would have to use a path of length 2 or
Right.
greater.
Okay, that makes sense.
Other questions for Fox? All right, nice job. And last up, first Euler circuit theorem. So, all right.
Yep, bigger piece of here. Alrighty, so what I have here is very similar to what Alex had. If an Euler graph is an Euler circuit, then the graph A must be connected. And I did this also by showing the A and B. So I guess you go with the initial statement that there is in fact a circuit, but it is not connected. And so because we're saying it's not connected, there exists an X, Y in this graph such that there does not exist a path from X to Y. Right, where X and Y are vertices, so for whatever reason, we've got one floating off in a different part of space. So because there is not, because there is not a path, this means that there cannot be a circuit. So meaning that this cannot be true, at least to a contradiction. Is that clear enough? I mean, I could draw a picture too if that's helpful. Okay.
You could also have just said, by Alex's argument, since every Euler circuit is an Euler path,
Yeah.
Alex's argument proves it has to be connected. And y'all are sometimes a little afraid to just cite each other's work when that's generally a totally legit thing to do.
Sweet. Alrighty. And then essentially this is Alex's work too, except we're looking at the case where it's an Euler circuit, so it must begin and end at the same point. So, I mean, we can go through the work again, but for your first beginning, vertex its degree, we'll name it A. The degree of A is 1 because you must leave that, plus 2 times the number of passes that go through it, right? It must approach it from a side and leave it, or approach it on an edge and leave it on another edge. And then you must also end on it, so there's one more edge that finishes on it, so essentially you end up with an even number, I can go through algebra to prove that, but I think we're okay with that. And then for all others, the degree is equals, that's not a super mathematical way of writing that, but that's gonna be like 2 times m, or whatever number you wanna say. So those are the only 2 situations that you can have. You have a beginning vertex, or you have some vertex that's in the graph that has a certain number of, kind of paths crossing through it, if you wanna think of it that way. So judging by that, there must be 0 odd vertices. Any questions? Sweet. Yeah.
So I just want to make sure I understand your argument correctly, Euler. So you're saying that the beginning/ending vertex definitely has to have even degree because, and then the intermediate vertices have even degree because for ones in the middle, anytime the path goes through, it also leaves. So you'll have 2
Yeah,
every
so,
time it kind of goes through.
I mean, the beginning, I guess I can even say and ending vertex. Maybe that's not being super clear either, but the vertex, everything must begin and end. You're gonna have leaving from an edge, you have a certain number of passes through it, and you must approach from another edge. Those are your options. And then for all others, you can't begin or end on them. So you approach it from an edge. You must leave so that the graph can, or so that the circuit/path can continue and end on the final one. That sort of makes sense. Does that answer?
Gotcha. I think so. Any other questions for Laura? All right, nice work. All right, good job, everybody. So essentially, what you all showed in this last packet is that if you have an Euler path, then you either have 0 or 2 odd vertices. And if you have an Euler circuit, then there can't be any odd vertices. That doesn't in and of itself guarantee, though, that you're going to, that if you have a 0 or say 2 odd vertices, then there has to be an Euler path. Or that if you have no odd vertices, then there has to be an Euler circuit. And so what we're going to be doing today is going to be focused around showing kind of the inverse, the B implies A to the A implies B of what Laura and Alex just showed. And, okay, there's enough for Dr. Troll to have one. We're going to do one example together before I set you loose on what we're going to be doing today. So, for example, we're going to look at this kite-shaped graph. So first of all, we're going to say that if you have a connected Euler graph, and say that an edge, E, is called a cut edge, if removing the edge causes the graph to be disconnected. Meaning if we were to just kind of erase that edge from our graph, suddenly our graph is no longer a connected graph anymore. So looking at this example, do we have any edges that if we were to remove that edge would cause the graph to become disconnected? Take it?
C to G.
This one?
Yeah.
Well, if we erased it, is this disconnected now? Why is that?
I can't can't get to G anymore. I guess if I start on the main part, or I can't get to everything else if I start at G.
Yeah, there's no way to get from G to any other vertex or vice versa. So I would say this edge here would be an example of a cut edge in this graph. Whereas if we looked at, say, any of the other edges, like say from D to F, if we were to remove this edge, we could still get, that still wouldn't affect our ability to get from any vertex in this graph to any other vertex in this graph via a path. It's just that to get from D to F, you kind of have to go the long way around instead of having an edge that takes you there directly. In other words, the interstate's closed for the day. You got to take some back roads to get from D to F. And I think this will be the only cut edge. So the reason why cut edges are going to be important to us is because we're going to have an algorithm, called Fleury's algorithm, for how you can generally come up with a Euler circuit or an Euler path for given some Euler graph using the notion of cut edges. So it's going to be called Fleury's algorithm, and you all have it in your packet, so I'm not going to write down each of the steps on the board. But what this algorithm says is, make a copy of the graph. First of all, see if your graph has any odd vertices. If it does, start at those vertices. If not, pick anywhere. And then from there, you're going to follow a path in your starting from whatever starting vertex you choose. And the key thing to your path is that you can only traverse an edge if it's not a cut edge, unless you have no other choice. Only take a cut edge if that's the only edge left at your vertex, meaning your vertex has degree 1. And then keep going through your graph, erasing each edge as you go through it. And then at the very end, you just stop whenever you can't traverse an edge anymore. So let's try that out here. Let's go ahead and label the edges, I guess. Do E1, E2, E3, E4, E6, E7, E8. So right off the bat, what would be a good vertex we could start at if we wanted to start at an odd vertex here? Awesome. Holly?
A1.
At A1? You mean an A up here?
Oh, why did I say A1? Yeah. I was looking at E1 and I said A1.
Oh, okay. Gotcha. Yeah. Yeah, the vertices are single letters. The edges are all E with the subscript. Yeah, I count 1, 2, 3 edges coming out of A, so I think that would be a good one. So we're going to do a path. We're going to try one of these paths that starts at A. Okay, there are no cut edges coming out of A, so I think we could take any edge that we want. Lori, what edge would you like to take out of A?
E1.
Okay, let's start going in order. All right, so we're going to take E1, which is going to take us to B. And as we traverse, we're going to erase that edge. Adam, where do you want to go from there?
E, take E3.
E3 to E?
Yep.
Isn't that taking a cut edge, though?
Oh, wait. Does the cut edge refer to the one that we erased, or?
It's cut edge at this point in time after we've already erased one.
Where else is he gonna go though?
Ah, we have no choice, so we have to take a cut edge here. So generally, we can't take a cut edge unless that's the only edge that's possible. Okay, so let's take E3. Down to E. Oh, our graph's now disconnected. Well, nothing we can do about that at this point. Griffin, how about from E?
Yeah, I think E4, taking E4 to C is the only option we have because we don't have any odds.
Unfortunately, at this point, we have to now take a cut edge again to get to C. And now that we're at C, it looks like we have some options. Helen Mariah, where would you like to go from C? E7, go back up to A. Are you sure this nice juicy E8 doesn't entice you?
That is a cut edge.
That is very much a cut edge, and in fact, if you took that one, we would be stuck and couldn't keep going. So, okay, so Helen Mariah wants to take E7 back up to the vertex A. And then I'm going to stop doing this exercise because from here there's only kind of one possibility left, which is we're going to take E2 to D, we're going to take E6 down to F, we're going to take E5 back to C, we're going to take E8 to G. And that is Fleury's algorithm for finding a path. What type of path did we just make on the original graph? So if we connect everything back up, put back the edges I just did.
Would it be just like a regular Euler path?
Yeah, we found an Euler path. And here's the kicker. It's going to turn out to be the case that as long as you have a connected Euler graph to begin with, and if the number of vertices is either odd vertices is 0 or 2, this will get you an Euler path every time. So by starting at an odd vertex if you can, only taking cut edges if you have no other choice, as long as you have one of these graphs that have 0 or 2 odd vertices, which according to what Alex proved earlier is the only possible time you could have an Euler path, this gives you a way to generate Euler paths. All right, I think that's enough. Let's get you all into groups. Dr. Trelaw, I have a question for you. What is your favorite way to partition a class into groups of 3 or 4?
I write a simulation. Do whatever you want.
Do what I want.
I'm the lead instructor for the class.
Oh, but my lead instructor act is, since I've been doing this all semester and have been running out of steam, I make my students decide for me.
Jacob should decide.
Oh. Okay, Jacob. All right, Jacob, how are we splitting up groups today then?
Gosh, this has happened before.
I was gonna say, it's not the first time I've picked on him.
I'll put. Oh gosh, it's not gonna work out. We'll do U3, us 3, U3, and U4.
Okay. Look at that. Nice. So easy.
All right, we'll do that then. All right, everybody get in your Jacob assigned groups and have at it. So in this packet, you're going to be looking.
How did that happen?
Yeah, what a coincidence.
That was a test.
So I'm tempted to break this up. No, I'll allow it. So for this packet, the main purpose is going to be to look at some examples of applying Fleury's algorithm and then seeing if you can use Fleury's algorithm in a way to help prove that if you have 0 or 2 odd vertices, then there exists an Euler circuit/path respectively.
How dare they?
Yeah,
Oh, you have to draw one next to it. Trace on it.
Oh, I like this actually.
also, Jacob, I think you forgot someone in the class who's not in a group.
Oh, Dr. Chalor?
That's one way to do it. I just.
You can be added to mine.
Don't worry, I see it already. Have all these.
Oh, let's go. Oh, I like when there's pictures. Me too.
Like one that has pictures and not proofs to
Yeah,
it.
the last one didn't have enough pictures.
Yeah.
Too many vertexes. I'm just gonna start saying that. It's more funner to say vertexes.
It sounds correct if you're not in that. Like,
I was
this
It
is-
does sound pretty cool. I'll give it that.
Yeah.
I wasn't thinking, I didn't even notice it sounded.
I didn't notice either.
It's just more funner
I
to say
know.
vertexes.
I guess should we like?
Yes, I have
Do
completed.
your path. Vertex. Down in Vertex, this is the way we do things.
There's a math joke in that.
Okay. Very
Plus one.
Oh darn it.
I'm glad we had each other.
I need to use C2.
Too hard.
No.
Well, the power of
Is
teamwork.
there any odd ones? that we
That's
should-
not
it,
right?
First one?
Yeah.
Yeah, there's
Okay.
an odd one there.
Just wanted to make sure. Alright.
Oh, yeah.
Right now, there's a department that
Right.
says,
Right.
children, there's
Yeah.
ISC.
I'm just gonna cut across them off.
It's all about like the self, how the self.
But it's okay.
I don't know what's happening with stuff like that.
I don't know.
Let's
figure it out.
See, I labeled mine according to the path I
first.
was gonna take.
One of the self is
Wait, that's what I could do.
Well,
Yeah,
I
I
didn't
know
write that
I'm
far.
sure.
It's my thoughts.
I
Yeah, I guess I just did like.
It was gonna be any, but I ran out of space.
You ran out of vertices.
Yeah, well, yeah. It was gonna be math, but math had too many of the same letters.
Math, not math. Creative Vertex labeling going on. See?
I just kind of like labeled my edges 1 to 9. That's order I used them.
Wait, you got 9?
Yeah.
Let me go.
Oh wait, no, I do have 9. Never mind. I was wondering where you
I don't know if I
back
actually like all this kind of I do, but I
Don't know if I actually applied it properly.
Not sure if you applied the algorithm properly, Laura?
yeah. I don't know if like, cause I didn't like erase. I don't know if I actually.
If you don't want to erase, you could do something like sort of what I did, and kind of like
That's what I.
scratch it out.
Oh, that's not what I did.
Put some barbed wire on it so that edge can't be taken again.
Oh, okay.
So, I was doing this one, but I started at this point, and I don't actually know if it's possible. But it's interesting because I thought that was on the
Because I got a path. Like, I don't think.
But at least maybe I just did it wrong.
At an odd vertex.
Oh.
Yeah.
I think I'm not getting anything on this.
I know my brains are cut edges.
Oh wait, I
My
think I
brains
figured
are
it out.
okay, well then
Well,
I'm
then
done.
like stick it this little area.
You only have
Did you apply the out?
I'm doing my best.
And then if they're the only one you can take.
It's a
Doing
little
my best, okay? Doc?
Like, it doesn't matter, like.
Yeah.
I was gonna say, I was able to get one out of this bottom one using Flurry's out.
The,
Oh wait,
the,
you already did it right.
wait, did you start there or did you start there? You start at the inside on or the
You
outside?
should be able to start at either.
At either.
I started at the inside one and ended at the outside one, but you could just as easily do my path in reverse to start at the outside one and end at the inside one.
I think I'm figuring it out. Did it form?
Still doing okay?
I think so, yes,
Well, the thing is, you can, but it isn't necessarily.
I got a pen.
So wait, are we just not allowed to go down an entire path that leads in a cut edge? Because that makes a difference, I think. Because suppose I took, so I go down
Sorry, I
here
called
and
this
this way,
one.
this zigzag. So this takes out like
Is it not
all
Vertex?
of these edges, and I get to this
That one
point
also
here,
on?
and if I go
One,
this
two,
way, it ends
oh,
up
four.
prematurely, but if
I'm
I
not
go
being dumb.
this way,
It's been a long week.
so like it
It's
has to
too
go
long.
We're all sitting.
It's been a long semester.
It's not over yet.
There's no long
It's a really long
Yeah, well.
semester.
Yeah, I'll find out later.
There wasn't any too long quarantine.
Everything's going up.
The algorithm.
Last year, yeah,
I like the sound of that.
Quarantine, came back, had a break, came back from break and quarantine, and then we went out, right?
Oh, yeah, because you're like the basketball team, and then they all got.
Yeah, like,
I think your issue is that you just
I
said.
remember that was rough.
That's
It was
terrible.
really
Didn't you all go to
terrible.
someone's cabin up north or something?
I didn't, I went home because it was, because I was already up.
Well, I understand how I could get a complete thing. I just don't understand why.
Wow, I wish I could be
Well-
quarantined.
Like, I'm sure it was a mini vacation.
I just, yeah. I got quarantined this semester for the first time. Just my problem staying in my room. I could write it on the board too.
Say we went to
But, so I
Florida,
started
we
here.
were quarantined.
So here,
way to do
here, here. Here, yeah, you spell out math, it's not too hard to follow. And then so I'll spend time So I choose to go this way. And so technically, there's no good edge if I take it either
I
way.
really can't believe
But
that.
this is a path that ends in a cut edge. So should I take this one in preference to this one because this path ends in a cut edge?
Let me take a look. Oh, okay.
Just like eating myself
I
out.
think if you take this
Wait, no,
one first, then
One, two,
your
three.
graph suddenly
Yeah,
becomes
sorry, I'm
disconnected
sorry.
because
Yeah,
then these
it's
four kind of get
It
isolated
sounds
from
right.
everything that's left.
does.
Right, but I don't, is there necessarily a rule about that? Or like
Yeah,
whatever?
can't take a cut edge unless you're forced to.
But this, it isn't necessarily
I
a
think it
cut
has
edge,
something
it's
to
just a
do
path
with-
that leads to a cut edge.
Yeah.
Actually, mine's
I would argue,
Mine
I don't know how to
this is a
use
cut
this.
edge. Right now, you have these three edges.
Because I'm thinking like how
These two edges down here,
we
and
did the
that's the
same.
only way to get from one to the other.
Isolate the rest of the graph, not
like
just
2K
necessarily
to
one
go through all
vertex.
of them
Exactly.
in between.
Yeah, when I say
Thinking
cut
like
edge,
that.
it doesn't mean like it only necessarily leaves a dangling vertex, one dangling vertex by itself. It means disconnected in the sense
Graph
that
connected.
suddenly you have at least two vertices that can't be connected, maybe because they're in
Flurry's
different
theorem is like
Comes back.
portions
an
of the
Euler
graph.
graph G is connected has either no odd
So does
vertices
that
or
make sense?
exactly two odd vertices. Flurry's algorithm produces an Euler path.
That's
So this, I think this is kind of like
Right.
it's contained by the theorem.
At this point, you have,
If an Euler
at
graph
this
is
point, you have
connected,
enough
it has
tools
exactly
fully
two odd
solved
vertices.
for this code.
Then, so it's like, the
You did have
hypothesis
some
is the
last
same.
time.
Then the algorithm applies.
Yeah,
Guys,
the hypothesis is the same.
That's not math.
the math. It's like not math.
I've been
The
having a lot of
hypothesis
math.
of
Yep.
Yeah, Zooks and Calvin and Hobbes.
Is that originally from Calvin and Hobbes, Dr. Choler?
Seems like that's old.
I was gonna say, Gadzooks is kind of an old fashioned. It wouldn't surprise me if it was.
Okay, because I think that's the only thing I've ever
One
read.
of my housemates sent us.
Golly,
The requirements or
I don't know where it's originally. Right.
the
Might be
conditions
from
of Flurry's algorithm.
This Euler graph is connected because exactly two odd vertices. And then it has an Euler path. Like,
Awesome, I can tell you from the name of an old video.
Seriously?
Wait, is that actually in the definition?
is it so different?
On those Genesis.
All it says is
What?
explain
How old
why.
was Genesis? Sega Genesis?
I was
Yes.
Flurry's
Awesome, I'm pretty sure.
Tissue.
Awesome Possum and the something of Dr. Makino. Came about environmentalism.
Says must begin in an odd vertex.
Yeah, I'll have my fun back here.
Oh,
Okay.
we
I think
are
that's
so
the
much,
first one.
so lit right now.
Oh,
you can't, oh.
I had to recover after I miscounted. I
By
started at A less, I'm like, A is odd.
website Onyx's biology.
Alex's proof says that the opposite of this, that if it has an Euler path, then it's connected.
Origin.
Would say that if an Euler path is connected, has
Not
exactly two
close.
odd vertices.
It's
Euler
the
path.
mills by which Christ was fascinated.
I think it's Fleury's theorem on the front page. that you want
Late
to
17th century.
Well, I started with Fleury's theorem.
That's not quite Calvin and Hobbes. I'm no history
So I have
major,
that
but
by Fleury's theorem,
Maybe
that
that
they
was
must start at an odd vertex.
That's how would we
know if it
I
wasn't
don't know.
Specifically, the algorithm
is
will.
about the size of Hillsdale in comparison to the United States, so.
I'll let you think about that.
Have an expanding vocabulary because you make up your own
I
words.
do make up my own words.
Which is arguably more fun.
More fun.
I genuinely have no idea what.
I just was like,
It's more gooder.
Exactly.
I guess we
the
can
goodest.
The yardstick is
It's
over
the
there.
goodest. My what?
So the yardstick is over there.
Are you scared?
you have to start and end by like the first.
I'm scared, you're acting very scared right
I guess
now.
if we erase like.
Well, the ends look kind of sharp. I was like, I don't need to lose an eye today.
That's true.
Edge.
Very careful with your movement.
Then again,
Do
like,
we have to say
And
so?
add an odd vertex.
Hypothesis of the second path theorem, same conditions.
Probably.
I think
I'd say Fleury's theorem, but then you could say Fleury's theorem says that Fleury's algorithm will produce an Euler path.
Everything
Dr. Gersh's like,
Mhm.
I'm kind of confused on the difference between the two.
Oh, yeah.
I mean, like, I can't put it
Between
in
these
math
theorems?
terms.
I haven't.
But if you have.
So basically, it's saying that basically,
I have all my exams to take home except one.
if you have no odd vertices, then you have the Euler path that's also an
So you
Euler
have to
circuit.
have.
If you have two odd vertices, then that's going to produce an Euler path for you. But by
I guess we could say that
Passing through for
it's basically so the first one. Let me.
if we just make it so.
I'm gonna start labeling and I'll
So the first Euler path theorem says if you have Euler path, then it has to have
Oh, it has an Euler circuit.
2 or 0 odd vertices. But the first theorem by itself doesn't say anything about the other theorems.
That's because you've been born after Ferris Bueller's Day Off.
Well,
Your brain is inherently programmed to
This is like when you said
Euler,
Basically, the second Euler path theorem,
it has to start and end at the same
When
time.
you get used to
And
it.
so when we
it's basically saying the
traverse
same
through
thing,
every.
but in reverse. That if you have 2 odd vertices, then you have to have an Euler path. And so together, they basically say something
I
along
was
the
that way
lines
to
of
write out, like I totally understand
Euler
one
path.
last
If
night.
you have it,
That's such a train wreck. I thought so.
No, but I'm like, I grew up with like,
just from the first one, that's not enough guarantee.
like you have to leave the, like, leave
the
original,
path.
get back to the original,
It just says that the set of all
go through
Euler path
to go to every.
is contained in the set of all 2 or 0 odd vertices.
2K for everyone.
Does that make sense?
Yeah.
I don't know what else to.
Oh, hey, Dr. Tor's leaving because class time's over.
Oh.
So we're gonna cut things off here for today. This was, so on Friday we'll do presentations on this packet, and then the second half of class, we'll talk about whatever you guys feel like.
Nice.
I have a question.
What's up?
I just asked Dr. Triller to give me an answer. When does your brain stop reading Euler is Euler? Because every time I read it, it's still.
Euler and Euclid? When does it stop?
Do you read it as Euler now?
I do, but I also read Euler for a very long time.
When does it
Okay, I
stop?
feel.
Did you
I think I was honestly in like grad school for me.
Did you watch Ferris Bueller's Day Off before you corrected yourself?
Euler.
Because that one scene in Ferris Bueller's Day Off will inspire generations of.
I have seen Ferris Bueller's Day Off, but it's been a very long time since I've seen it.
That's sad. Maybe we'll talk about that on Friday.